All right, Bismillah Rahman Rahim. Can you see my slides?
Yes, sir, we can see your slides.
Okay, thank you. So I'll just start right away. Thank you, everyone. The title of the talk is Agent-Based Models to City-Scale Digital Twin. So I'll be talking a little bit about the past experiences and current challenges. It's a quotation from Imam Malik, which I like. Knowledge will not come to you, it's you who should come to the knowledge. And by the way, this is the library in Oxford University, Bodleian Library, which is the largest library. And it is also very old, perhaps oldest library in the region. So I have already been introduced well. Thank you, the host. Just a little bit. I am a postdoc at Oxford University in the Department of Computer Science in the Artificial Intelligence and Machine Learning group. And I'm currently working on the Large Agent Collider, which is a funding received by UKRI and Alan Turing Institute. So the idea here is to work on robust agent-based modeling at scale. I am also a tenured associate professor at NUST University in the School of Electrical Engineering and Computer Science. So I will begin my talk with an opening perspective and a bigger picture of what are we doing here and what is this talk about. So there are 5 trends which have been very prominent in the evolution of computing: ubiquity, interconnections, human orientation, intelligence, and delegation. So when we talk about ubiquity, you can see that there are so many things in which computing is made appear to be at any time and everywhere. And also we call it pervasive computing or ambient intelligence. So ubiquity is about computing being everywhere and at any time. So computer systems are widely interconnected. So that's one of the bigger prominent evolution of computing. In human orientation, initially the computer systems were very difficult to interact with, but the human orientation is a focus in which computing has become very human-oriented. So you can see this evolution. And the ability of computers to learn. And the ability of the computers to learn a specific task from data and experimental observation is the intelligence. And delegation is about having computers perform tasks on the behalf of human beings. Like this is a picture of Google car, which is a driverless car. So when we talk about the emergence of artificial intelligence, we can divide this into 3 main clusters, one of which is data science, the other one is the machine learning, and then the artificial intelligence. And how they are related is data science is basically the processing and transformation of data. Machine learning is basically known as an engine that helps us work on the artificial intelligence. And the actual part, which is related to the artificial intelligence, is actions. And that's where, which is the most important part. And currently, we have insights that are the predictions of machine learning algorithm or its processing of data science to be able to have informed human decisions. But we are moving towards an era where automated decisions needed to be done. And this is the most important part in the evolution of artificial intelligence. Having said that, an AI system that are ubiquitous, for example, the presence and intentionality of system is there. So systems are not only reactive, but they are more intentional and deliberative. That's important to note. They are interconnected. For example, the systems can have cooperation, coordination, communication, and even they can negotiate on behalf of their users. They are understood. For example, they are programmed via human-like metaphors. So it's easy to program them in a way human program, and they are like they are understood. They are intelligent. For example, they can decide, sense, decide, and act. And they are autonomous. For example, act on our behalf. So all these things, they lead to us to the era of agents. And that's where we are going to discuss it further on the topic of agents. So critical examples, typical examples of agents could be seen in NASA space rovers or Amazon robots, where the systems are not only intentional, they are deliberative, and they act and delegate tasks on the behalf of humans. So in the opening perspective, one thing is clear that this leads us to the study of multi-agent systems, where a multi-agent system is a system composed of multiple deliberative interacting intelligent agents. An agent is a computer system that is capable of independent autonomous actions on behalf of its users or owners. So this book is written by the principal investigator of our project here in Oxford, Michael Woodridge. He is also my boss, and he is actually the main person who has been working on this field of artificial intelligence for over 3 decades. So let's talk about agent-based modeling and simulation, which is the primary focus of this talk. So when we say risk-free world, what does it mean? It means that delegation and distributing autonomy among agents, among systems is not a trivial task. So when we are trying to implement an artificial intelligence system in a futuristic way, we basically are thinking to deliberate and distribute autonomy among the systems. So, but it is not that simple. In many cases, we can't simply afford to find the right solution by experiment with the real world. If you remember, there was an incident in Germany where an automobile car manufacturing robotic system was able to kill a person. So that causes a lot of issue in the concept of using AI. So that's simply because it's dangerous. Building or destroying or making changes may be expensive, dangerous, or simply impossible. For example, if we talk about Mars rover, it is impossible to study that here on Earth. The main goal of modeling is to find the way from problem to its solution through a risk-free world. That is simulation. So the simulation is basically an environment in which there is no risk, and we can experiment with different things. So complex systems. Modeling real-world complex system is a challenging task. Complex systems generally have 3 attributes. A complex system is made of many parts. It has units, individuals, or subsystems. For example, in an energy system, we have a power generation plant, we have transmission grid, and we have also the entities that use the power system. So there are many parts of this complex system. There are many relationships, interactions, dependencies, or competitions between these parts. And the parts produce combined effects, for example, emergence, that may not be easily seen if they are alone, and may often be novel or chaotic. So the 3 key properties of complex systems are having multiple parts, relationships among those parts, and the combined effects. ABM is identified as a suitable modeling technique to develop and model conceptualize complex systems. At its heart, it is aimed to model system-level patterns that emerge from interactions of individual agents with their neighboring agents and the local environment. So I'll skip a little bit of these details because I want to come to this slide, which is elements of ABM. So there are 3 main essential elements of agent-based models. One is the synthetic population. Since we are talking about agent-based simulation as risk-free, so we need to develop synthetic populations that will be simulated in an agent-based environment. These could be persons, vehicles, for example, charging stations or daily operations of the real world. So synthetic population is an area in which the ABM modeler basically try to develop a population based on daily life operations. The second important element of agent-based models is virtual environment. That could be GIS-based systems, it could be conceptually a grid system, or it could be simply a Cartesian 2D XY coordinate system. So if we're talking about complex system, we would like to have GIS system in place with some traffic routing or mobility of agents in that environment. And the third and important part of the ABM is basically behavioral rules or rule sets, which defines the change of state of agents in a logical way. So all these three components are united to form an ABM. Let's talk a little bit of some past studies that we did in the area of agent-based modeling to capture complexity of real-world systems. The first one that we did previously was an ABM on household electricity consumption. So as you know, this was a study conducted in Islamabad city. In a particular sector, we simulated n number of houses, where houses have households, which are families, and families use electrical appliances to basically switch on or off to do energy consumption. So this is a hierarchical agent-based simulation in which three types of agents are interconnected with each other. So I'll just simply give an overview of what happened here is that we simulated 24 hours period of device level electric consumption of typical houses in an area of Islamabad, which was correlated with temperature, and the energy load was simulated using an agent-based simulator. So an application of ABM was conducted to basically forecast the demand of electricity at household level. Another study was done on water consumption, which is also a key problem in Pakistan. So we had Nust housing. So I was residing in Nust, and our study was related to some 300 houses of residential areas in Nust University. So we collected data. So this ABM has a special feature, which is basically connection of the demand and supply, and the study of demand and supply gap using ABM. So in the demand side, we simulated different water consumption activities of a person during the day in a typical household of Islamabad. And that could be usage of toilet, shower, washing clothes, kitchen, and all the other kind of water-related activities. And with that simulation, we came up with the with the projection of daily demand. And this particular chart shows activity-wise demand of water consumption, which is basically an interesting insight. And this is a main potential and advantage of ABM. So ABM can give us a micro scale insights of a system rather than a macro level overall projection. So when we talk about micro scale, it could be that we can project activity level water consumption of household areas. A similar study was done in Islamabad city on urban waste management. So we basically simulated the transport vehicles of which carries waste from CDA to the landfill, which is somewhere closer to the I-9 sector in Islamabad and back. And this whole study was done to study in engineering design, which was the implementation of IoT on smart waste management systems. So if the dumpsters which are located, these green dots are the dumpsters which are located at different parts of Islamabad city. And if they are green, that means they are filled. And if they are red, they don't need to be picked. So with the help of IoTs, we can save fuel and cost. And this study was basically aimed to, so instead of implementing an engineering design into the real world and invest a lot of money, we first simulate that design in a prototype. So this agent-based simulation was basically meant to test an IoT-based smart waste management among dumpsters across Islamabad city. And this basically chart is a representation of the smart dumpsters and the ordinary dumpsters and their optimization in terms of saving, reducing distance of travel and saving time and fuel. So another agent-based simulation that we worked on was an interesting study on emergency evacuation, which was a Hajj scenario. So we collected some masjid dimensions, and we collected these geographical dimensions and constructed a pedestrian simulation model that was simulated to analyze the evacuation of agents which were Hajj pilgrimage at this time. And we invested a lot of effort in trying different types of optimization techniques for the evacuation strategies, to study evacuation strategies across this Masjid al-Haram. So this is a very interesting application of agent-based modeling to study emergency evacuation of pedestrians or maybe the vehicles from the city at a large scale. And a similar work was conducted on the building level evacuation. So this is a SEEKS building of NAS School of Electrical Engineering and Computer Science. And this building has some 3,000 to 4,000 of agents residing at different locations with their types. And the idea was to basically analyze different evacuation strategies. For example, there are different exits at this SEEKS building, and once we simulate these evacuations, we can figure out the optimal evacuation strategies. And we validated this by collecting real data of the emergency evacuation drills that we conducted on ground. Another application in the past that was an engineering project on wind power plant, where the agents were the components of a wind turbine. And the idea here was to simulate a large-scale wind power plant, which was actually, this project was collaborated with a company, I am forgetting the name. So that company had given us some data, and we simulated, using agent-based approach, we simulated wind power plant and calculated the projection of the forecast of energy generated from that power plant and validated it with the help of real data. Another project was forecasting of dengue spread across Islamabad. This project was basically used to simulate the spread of dengue across Islamabad city based on some initial information collected in the form of data. So there are two types of agents that were simulated here in this project. One was the mosquito and other was the human population. And both types of population were interacting with each other in the simulation to produce effect, which is the spread of dengue. Another project was conducted on an interesting area, which is basically refugee migration, and it is one of the biggest problem in EU, especially. Also considering the current situation of Ukraine, and in the past there have been so many issues in which the refugees are forced to migrate. And this project was basically targeting, it was done with the collaboration of Institute of Migration and UNO. So this project was basically targeting the projection of refugees which were developed in the form of agents and their behavior in terms of fleeing towards different safe locations in the context of forced migration. Another project was forecasting of COVID-19 in UK. So this is a typical snapshot of the simulation that we produce for the forecasting of COVID-19 in UK in 2020. And this is a particular borough. This was basically a project in which we scale up a large level of agent-based population. It was roughly multiple million, like 2 to 3 million of agents across the city. The total population currently in London is about 6 million. And the target was to be able to have a computational complexity of a large-scale simulation, which is geospatially rich and scale and on a real scale. So we should be able, we were able to deploy our simulation on supercomputing environments for a large-scale simulation. So this is where the whole idea of city-scale digital twin came into being. So what is city-scale digital twin? A little bit about it. A digital twin is a virtual representation or replica of real-world physical object or a system. So we have an aircraft engine. If we construct a digital twin of that engine, then we can work on. So it's basically a replica in the form of a simulator, which basically works just like a real world system, and it is connected with the help of input data and feedback loop. So whatever changes that are done in the design level are applied in the real system. So this is how it's called. That's why it's called a twin, because it works together. They two work together. So the concept originated from NASA's physical twin, in which they created the third rover, which was planted in a laboratory in NASA, which was connected to the actual rovers in Mars, which were sent and to explore different geographical terrains. So this digital twin, okay, so I'll just try to wrap up. This digital twin was used to basically analyze different kind of situations. So it's a very useful area of research where people develop digital twins. Now talking about city-scale digital twin, the first city-scale digital twin was developed by Singapore, which was an entire 3D representation and simulated representation of daily operations of the Singapore city. And it was a very innovative effort by the Singapore University, NUS University, Singapore. We developed a digital twin, our first digital twin, using agent-based modeling approach for the city of Tampa in Florida, called Eden. So our digital twin was basically developed in a geospatial region, which is the city of Tampa, and it was developed using agent-based modeling approach. So on left side, you can see different types of buildings, which are geographically situated. And on the right side, they are clustered in the form of houses, workplaces, restaurants, warships, grocery, mall, school, outdoor, and banks. So these are the different types of building which we basically modeled by parsing a lot of GIS, spatially rich data, and constructed our digital twin. This shows the 3D representation of the Tampa city. Although 3D representation was not mainly used in the actual model, it is just for the reference and validation of the spatial features of our model. And this is the visualization of the simulation. The whole idea of developing this digital twin was to study COVID forecasting with the help of Department of Florida Health. And this particular visualization shows different agents moving around the Tampa city in our digital twin, in which blue agents are like healthy agents, the red are infected, and the black are basically, they are not moving because they are dead. So this change of state of agents is represented with color in the digital twin. And on the right side, we can see the heat map of the spread of COVID, which gives the hotspots of the spread. This is the layout of how the simulations of the digital twin represented and reflected the results. Now I'm going to close my talk and talk a little bit about the current challenges and opportunities in agent-based modeling. So the first and foremost challenge, sorry for that wrong title here. The first and foremost challenge is that we need dynamically large scale geospatial virtual environment. So in order to upgrade our agent-based models, which were typically developed to simplify a real world system complexity and just to analyze a part of that system in a simulated environment, now we are moving towards a very different era in which we want to basically using data science and machine learning algorithms. We are interested to develop a large-scale agent-based models which are spatially rich and based on real scale. So the development of virtual environments of that large-scale system needs application of deep learning approaches and automatic synthesis of virtual environments. The second area in which we are having challenges and we have a lot of opportunities is synthetic population with realistic agent behaviors. So we want to construct, for example, if you remember the talk in which I talk about the household water consumption, and we want to simulate daily activities of people who are consuming water. So there could be some novel ways of applying deep learning and machine learning approaches to develop rule sets which are not logical by programmatical They are not static because they are logically programmed in the system. They are more like dynamic, and they are incoming from the real data. For example, the census data or any kind of other data which is present. So this kind of approaches will make the agent-based models more realistic and more dynamic in terms of synthetic behavior of population. The third and the most important area is the model calibration. So it is very difficult to calibrate an agent-based model with respect to the real data, because agents, they are meant to be bottom-up in nature. And when the individual agents are having their own rule sets, which could be simplistic, and they are basically interacting with each other to emerge into a real system, which should reflect like a real world. It's very complicated to calibrate those models. And we are studying data assimilation and model calibration and parameter tuning approaches for ML, using ML for ABMs. And the last and foremost challenge is, very important challenge is verification and validation of ABM models. And formal verification approaches needs to be studied in these areas. I hope I finished it on time. Thanks a lot. I'll be happy to receive any questions.
Okay, so
I haven't seen anybody. Am I able to see any audience? Is the camera good? Can we see the audience now? Yes, thank you very much for the zoom out. Now I can see the audience, I think Dr. Budar is also there. Assalamu alaikum, Dr. Very happy to see you. I should mention that I am very happy to come back to talk to the people which I worked before. So HICS and UAE has been my former affiliation back in 2013. So any question from the audience? So I have a question, Dr. Imran. Can you hear me? Yes, please. Yes, please. Okay, so given the fact that we have a very limited types of industry in Pakistan, so where do you think this digital twin concept is applicable for the industry in Pakistan? I personally think that, so I will respond to this question in the context of academia, industry, and research link. So it's a triangle that we can keep in mind while I respond to this question. So we have been trying to work with Lunds University, for example. We received a grant that was related to two types of projects. One was in agriculture, where we wanted to study the economy, energy, and agriculture processes using agent-based simulations for the digital twin of a particular area in Pakistan for the study of circular economy. So that was one project where it is very applicable to design a digital
that could help as a tool in the area of agriculture for the economy study. And the other was air quality monitoring. This is still in place. It's not yet right, but we are thinking to basically to develop the Lahore digital twin and its multiple layers. For example, the transportation layer, the industrial layer, all the different types of layers to study the air quality index. And in the digital twin, our aim is basically to improvise different kind of strategies to reduce and to basically improve the air quality. So in the area of air quality monitoring, the application of digital twin could be very much applicable, I would say. As far as the industry is concerned, the concept of digital twin is very old, and it has been mainly in the aeronautical. For example, we had a collaboration with PAC Camera for the study of developing digital twins for JF-17 plane. In the study of, the application of digital twin is to improve manufacturing processes by working on digital twins and then implementing them in the real systems. So that is one area in which we have been trying to explore collaboration with PSC Camera for study of digital twins of JF-17. Then, yes, there are a lot many challenges in terms of real industry where the industry has lack of interest in innovation and designs. Instead, the type of industry we have in Pakistan is very different. So it's a long debate, but in short, we have been exploring a lot of different spots where we can connect digital twin technologies in the real industry. Main players in my what you can experience is energy systems, agriculture, this environmental studies, and aeronauticals. So these are the 4 players which I am thinking to basically work with for longer time.
So thank you, Dr. for your wonderful talk. So now we will actually switch to the next talk. So thank you, Dr.
Thank you very much.